everybody. Today it's a great pleasure to introduce Sergei Frolov to start the morning session, and he will tell us about tracing factors and thermodynamic Bethe-ansatz for ADS3, S3, T4. Please, the stage is yours.
Good morning. I'd like to thank the organizers for the invitation. I'm going to talk about three papers we wrote last year in December with Alessandro Sfandrini on dressing factors and TBA for the Ramon ADS3 cross S3 cross T4 superstring. And I'm going to talk mostly about the dressing factors paper, and if I'll have time, I'll also talk a bit about the TBA. If you will have questions, please do not hesitate to interrupt me. Let's maybe start. So this is the outline, and as you see, it's very simple. It follows exactly the title of the paper. To start with the introduction, let me recall why we are interested in this string series. And the reason is clearly in the ADS-CFT correspondence. And what we hope to do, we hope to solve the string theory sigma model to find the spectrum of states in the string theory by using this approach. And then by the ADS-CFT correspondence, this string energy, the spectrum of string theory, coincides with the spectrum of CFT operators in a dual theory. To find the spectrum, we need to, we use the TBA approach and use the fact that the thermodynamic of the mirror theory, which is obtained from the original string theory by using the double weak rotation or Matsubara transform, depending on what you like more, field theory or condensed matter theory. So the thermodynamics of the mirror theory determines the spectrum of the dual theory. So this is a nice approach, and it involves many steps. And again, let me recall what are the steps. So we start with the Green-Schwarz superstring on, this is the most common case, on ADS-P cross M10 minus P. It can be a more complicated manifold. What we need from this manifold is one time isometry direction, roughly speaking in ADS space or in deformed ADS space, and one space isometry direction in this space here. And then we can impose the light cone gauge. And then in the light cone gauge, the string energy minus the charge J corresponding to the isometry direction in this manifold M is identified with the light cone Hamiltonian and is given by this expression. So we have a theory on a circle with periodic boundary conditions, and then we take the decompactification limit where J goes to infinity and get a theory on a plane. And then once we got the theory on a plane, we should do the space-time exchange, the double weak rotation, and the space-time exchange, and get a mirror theory, also on a plane. And for the cases of interest, the resulting model is an integrable model in 2 dimensions, and it has 8 bosons and 8 fermions. The unpleasant feature of this model is that it has no 2-dimensional Lorentz invariance, which leads to substantial complications in comparison to the relativistic case. So, and then we have to analyze symmetries of the mirror model and use them to fix the dispersion relation and the matrix form of the worldsheet S matrix. And also we can then use the matrix form of the S matrix to derive the crossing relations for the dressing factors. And then we use these crossing relations to find the dressing factors, to fix them up to CDD factors. And the difficult part then, once this is solved, is to single out the right dressing factors, the ones which correspond to your string sigma model. So once it is done, once we understood, we have understood the mirror theory on a plane, we can use the S matrix to derive the mirror beta Young equations. So assuming that the size of the corresponding mirror theory is large. And then these beta Young equations are used to formulate the string hypothesis, so to identify which configurations contribute in the thermodynamic limit. And then once we formulated the string hypothesis, we use the beta Young equations and derive the ground state TBA equations. And they have this general form, which is valid for any known model. And y sub a here are functions associated to each of the string configurations. And I have a summation of repeated indices here and there. And E tilde, E epsilon tilde, it is the dispersion relation of these mirror particles corresponding to the string configurations. In some cases, it is 0 if it is auxiliary, if this corresponds to auxiliary roots. Sometimes it's not. So in this sum, we have only y functions which correspond to momentum carrying excitations. Okay. Mu are chemical potentials, imaginary chemical potentials in the mirror theory. They correspond to twisted boundary conditions in the original theory. And then, well, these equations can be used to derive TB equations for excited states by using the contour deformation trick, which is very simple. We just say that this star product, it's not an integral over a straight line. It is an integral over a particular contour, and that's it. So you choose different contours, you get different excited states. Otherwise, the form of the equations remains the same. So this program has been successfully realized for two models, ADS5 cross S5 string theory and ADS4 cross CP3 string theory. And one of the reasons why it was relatively easy to do it was the fact that in both cases symmetry algebras were simple. And as a result, particles were basically in one multiplet, and there was no complications related to semi-simple nature of the symmetry algebra. The next interesting case, it is a DS3 cross S3 cross T4 string sigma model. And well, it has, there are many different versions of this model. So, and I'm going to look only, as I said, at the case with the pure Ramon-Ramon case, Ramon-Ramon flux. We can also consider mixed flux case where we have also B field and SNS fields in the model. It is also integrable, but it's substantially more complicated. And it is not really clear whether the purely Ramon-Ramon case can be considered as a limit of the mixed flux case. Maybe it's not. Maybe it is an isolated point. Well, in any case, so this string sigma model, yeah, so as I said, strictly speaking, we are supposed to study mirror theory, but people are lazy, so they they just analyze the original string theory and then use an analytic continuation to understand the properties of the mirror theory. And that's, again, the standard route. And I'm going to use the same route here. So this model was studied by this group of people in many detail. And what I'm going to talk about now is a very short review of what they found. So they found the symmetry algebra. Well, actually, the symmetry algebra probably was found before you guys, but in any case, so the symmetry algebra of this model is the sum of 2 PSU1,1/2 plus this U1 to the 4th due to the isometries of T4. I have written U1 to the 4th, but I hope you understand that it is 4 copies of R. And then, so this is the symmetry algebra before we impose the light cone gauge. Once we impose the light cone gauge, we get and consider the decompactification limit. So we consider theory on a plane. Each of these PSU1,1/2 becomes a sum of 2 PSU1/1, centrally extended. And the central extension here is the same for both of these algebras. Well, nothing happens with this guy. But in addition, we get an extra symmetry, SO4 symmetry, which appears because in the decompactification limit, we lose information about the winding modes of the torus, and we can see only modes without winding. So effectively, it means that the torus T4 becomes R4, a four-dimensional plane. So this symmetry still kind of important. And then analyzing the representations of the symmetry algebra, it was shown that the fundamental particles, all fundamental particles transform in four-dimensional shorter representations, and the dispersion relation has this form. And so it is the same as for, say, ADS5S5 case. If you look at this dispersion relation, you can see immediately that it is the same dispersion relation as for a theory on a lattice with a lattice step equal to 1 over h. And h here is the effective string tension. This fact will be important later when we will discuss the consequences of the dressing factors we propose and compare them with perturbative calculations. So M here plays the role of the mass of these particles, and for fundamental particles, M takes values plus minus 1, so plus for left particles, minus for right particles, and name left and right does not mean that they move to the left or to the right. It rather refers to these guys, to these symmetry algebras. And then the mass can be also equal to 0. So, and the appearance of massless modes, it is the second. So the first unpleasant fact is that we have two different particles transforming into different representations, massive particles. And that's because the symmetry algebra is not just a simple one. And the second unpleasant fact is that we have massless modes. Or to be precise, we should have gapless. We should have said gapless modes because we have the sine squared p over 2, so it is not a relativistic massless mode. And in fact, this massless, I still will be calling them massless modes, but so these massless modes, they could have 0 velocity in particular. So that's the story. These massive particles can form bound states, and then M can take any values from minus infinity to plus infinity. And if I will have time to talk about TBA, I'll mention this in more detail. So because we have several particles, we will have these 4 distinct blocks. So the S matrix which describes the scattering of left particle, and there is a Z2 symmetry in the model, so this is equal to the S matrix scattering right particles. Then similarly we have a block which scatters left and right particle, and it is the same as the scattering of right and left particle. And then we have a scattering of left particle with massless, so this circle denotes massless particle, right particle also with massless particle, and there is also a scattering of massless with left particle and massless with right particle, but by Bragin unitarity they are related to each other in this trivial way. And finally there is a S matrix which scatters massless particles. And that's it. So we have 4 blocks, and as a result we will get 4 dressing factors. 4 dressing factors we would want to find. So, and then once these blocks are found by using the symmetry algebra, one can derive the beta equations, again up to the dressing factors which remain unspecified. And these dressing factors are satisfy crossing equations, and these crossing equations were derived, and solutions to these crossing equations were then proposed. Unfortunately, the proposal has several unpleasant features, and one feature which was not noticed before is that the proposed factors, so this sigma bullet and sigma tilde bullet, these are the dressing factors corresponding to sigma bullet to these guys, dressing factors for these blocks, and sigma tilde bullet for these ones, so for massive particles. So they in fact violate the parity invariance of the model because of unpleasant cut structure. And just because of that, actually, we can just say that these dressing factors are incorrect, because the theory must preserve parity invariance in the pure Ramon case. And second, the dressing factors corresponding to the scattering of massless and massive and massless particles, they contain the AFS dressing factor, which is the leading order term in the BS dressing factor. And the AFS dressing factor has very unpleasant analytic properties. And in general, you do not really want to deal with it if you want to solve the model exactly. So then, in the dressing factor, which corresponds to massless massive particles, there were additional apparent square root branch points whose positions depend on relative values of momenta of the 2 scattered particles. And that's also a very unpleasant feature, which makes it unclear how to do analytic continuation to the mirror theory, basically, and even to check the crossing equations. Okay, so because of all these properties, unpleasant properties, it was unclear how to analytically continue the dressing factors to the mirror region. And as I said, to find the TBA equations and the spectrum, we need actually to understand the mirror theory. Okay, so also the dressing factors which were proposed, they are not compatible with some of the perturbative computations, and I will. And this is probably because the computations, the perturbative computations which were done, did not use the right regularization, UV and IR regularization. I will talk about it later. The same problem we have in our proposal. So there is a disagreement between our dressing factors and existing perturbative computations. Okay, so now to be more specific, I use the sigma bullet bullet, sigma tilde bullet bullet, and so on, and they are related to these S matrix elements in this way. So basically, this is just necessary to fix exact normalization of the S matrix elements. And again, you don't need to memorize anything here. It doesn't really matter for what follows. I just want to stress that everything is fixed exactly, including all the signs. So so these formulas, they include x plus minus Zhukovsky variables, which are defined in the standard way by these formulas for massive and massless particles as well. And for massive particles, the formula looks like that in terms of the momentum, and I assume that P here is real. If P is complex, then we need to use some analytic continuation, and because of the square root, it's a bit ambiguous. For massless particles, we just set m to 0, and we will get this formula. And we see immediately that in this case, we do not really need x minus, because x minus is equal to 1 over x plus in the massless case. So we are going to drop x plus minus for massless particles and just use a letter x for massless particles, which is equal to x plus. And it is e to the I p over 2 up to a sign of p. Right? So imaginary part of x is always greater than 0. And for real p, it is on the upper half circle. And then the energy of massive and massless particles can be found by using this Zhukovsky variable, by using these formulas in the standard way. So, as I said, the crossing equations were previously derived. These are the crossing equations. And, well, again, they have more or less the standard form. They're expressed in terms of these Zhukovsky variables, with one difference. Well, for massive particles, actually, the crossing equations relate sigma and sigma tilde. The dressing factors corresponding to the scattering of left-left particles with each other, or right-right particles, and the dressing factor which corresponds to the scattering of left and right particle. So that's the difference, and well, we will see that it changes a bit the story. And then what is also interesting is that the dressing factors which involve massless particles, the crossing equations which involve massless particles, they all are expressed. The right-hand side of these equations depend on this function f, one and the same function f. And this function f is defined in this way. And it satisfies the crossing equations with the -1 sign. And this function will play a very important role in what follows. So, okay. So we know that in the ADS5S5 case, the solution of the corresponding crossing equations was given by the BS dressing factor. So it makes sense to strip out the BS factor from all the factors we have. So we take our factors, we divide them by BS dressing factor, and we get this new var sigma factors. So the BS dressing factor was defined for massive particles with mass 1. So for massless particles, we define the corresponding BS phase by considering the limit where x2 plus goes to x2, x2 minus goes to 1 over x2. So by taking the corresponding Zhukovsky variable to have massless kinematics. We can do it because in the definition of the BS dressing phase, x plus minus can be considered as completely independent. So there is no need to impose the corresponding constraint on these parameters. So in this way, we will get this new BS factors. And well, the BES factor satisfies a known for massive particles satisfies this crossing equation. And then this equation can be obtained from this one just by taking this limit. And in addition, if you consider the crossing of the massless particle, we will find out that these BES factors satisfy just homogeneous crossing equation. We get just one. Strictly speaking, it is our prescription for the analytic continuation of this guy to this anti-strain region. Okay, we can always choose a crossing path such that these equations are satisfied. And they are very important. And you see there is a very noticeable asymmetry between this and this equation. So once we this do, it is convenient to introduce this var sigma plus var sigma minus, the product of sigma and sigma tilde, and the ratio of these guys. And then the crossing equations we had can be rewritten. And for var sigma plus, we get a standard crossing equation. And we see that actually all these equations now are expressed in terms of this function f I showed before. And then for sigma minus, actually, we will get not a crossing equation, but the monodromy equation, which depends on the u rapidity variable defined in this way. Okay, so, and we see immediately that the right-hand side is completely factorized. So it is natural to look for a solution which would have a similar factorized form. Okay, and looking at these equations, we see that this is kind of for massless particles. This is the simplest equation. And if we take kind of a square root of this equation, we just get 1 over f. So it makes sense to look at this equation. So I use the formula for f, and I get this. And then I follow the proposal by Fontanelle and Torrielli. And they made this very, very important observation. They found out that if we make this substitution, if we introduce a new variable gamma in this way, then this function becomes equal to this function, I tangent, hyperbolic tangent of gamma 1 minus gamma 2 over 2. So the right-hand side of the crossing equation becomes of a difference form. In fact, the matrix part of the massless S matrix is also of a difference form. So from this point of view, it looks basically as the usual relativistic theory now. So, well, now if we use the formula for the energy and for the momentum of these massless particles in terms of gammas, we can see that, and if we use the fact that under crossing transformation P goes to minus P and E goes to minus E, we can see, and X goes to 1 over X, we can see that to get this, we can either shift gamma by plus I pi or by minus I pi. So we need to fix the sign, whether it is plus and minus. And to do it, we can use the fact that the real mirror momentum should be between the strain and anti-strain real lines. Okay? And once we do it, and we also want the energy of the mirror theory to be positive, so once we do it, we find immediately that the correct shift corresponds to the plus sign. So gamma plus I over 2 pi gives us the mirror theory real line. And the crossing transformation as a result corresponds to the shift of gamma by plus I pi. And I'm talking about massless gamma at the moment. So, and the mirror transformation is this one. So this is a picture. So this green semicircle corresponds to physical values of the momentum. momentum of a massless particle. This orange one, it is anti-strain physical values of the momenta. And this line between -1 and 1, this is the values of the real mirror momentum. And on the gamma plane, this green semicircle corresponds to this line, real line also. This one corresponds to this line, and this segment corresponds to this line here in between of them. So when we move from string theory to anti-string theory, we move like that, and we cross the mirror line. Okay, so that was the story. So now we can write the equations in terms of this gamma parameter. And the equation takes this simple form. And in fact, this equation has been known for many years. And the solution to this equation is given by the Zamolodchikov's S matrix for the sine-Gordon dressing factor. So it can be written in this form, like that. So it's a product form. You can also write it by using some integral representation for real values of gamma. It's not really that important. What is important is that it satisfies exactly what we need. What is interesting is that there is a relation between this sine-Gordon dressing factor, which is given by this formula. So minus phi to the fourth is equal to e to I theta Hernandez Lopez of x1, x2. Well, we can't take the square root of it because there is a plus minus ambiguity if we do it. So this is the exact relation valid for all values. If you take the square root, then you would have to remember about plus minus sign. Again, this relation was found by Fontanelli and Torrielli, and was one of the motivations for, I guess, using this sine-Gordon dressing factor. Okay, so that's nice. Questions?
Yeah, is there a first principles reason you could have? Is there a first principles reason you could have decided that this S had to be of difference form, rather than explicitly solving it and realizing its solution is of difference form?
No. Well, actually, this S is of difference form because there is no reason to have something else, right? The right-hand side is of the the right-hand side is of the difference form, so we can always find a solution which would be of the difference form.
But,
but a priori, there is no reason. It could be anything you want to. Yeah, definitely. It's just the simplest solution. Yeah. No, S is just some function. So I consider this equation. It is not the crossing equation. So let me stress. Yeah, let me show again the crossing equation. This was the crossing equation, and it has minus 1 over f squared. And I consider the equation where I have just 1 over f. I want to introduce Zamolodchikov's dressing factor, right, in this way. Once I do it, and once I remember my original crossing equation for the massless particles with the minus sign now, I see that I can solve it by using a function a of gamma 1, 2 times this phi squared, the Zamolodchikov's phi squared. And this function a of gamma must satisfy this crossing equation with the minus 1 on the right-hand side. And then it would also these conditions, right, which follow just from the unitarity conditions of the model. And the simplest solution for such a function is given by minus I tangent, hyperbolic tangent of gamma over 2 minus I pi over 4, which has these asymptotic conditions, which are also very important to match the dressing factor to perturbative calculations.
But nothing here depends on string tensor. The S phase depends on string tensor. But this
Precisely. This, well, it depends because, well, it's a question, it's a very interesting question because it depends on how you define your objects, right, your variables. If I use gamma for everything, then you are right. Yeah, nothing depends on tension in this path. Only the BS phase depends on the tension. But if I use, for example, a rescaled U variable, the one which people do in quantum spectral curve like, yeah, where U is shifted by I over 2. Yeah, then I will get it somewhere else, right? In any case, here in terms of gamma, there is no dependence on the string tension. And actually, this prefactor also appears very often in relativistic models, which describe also scattering of massless particles. So it is also very, very well familiar guy. So in any case, to summarize, the massless dressing factor is given by this expression. And it differs from Fontanella-Torrielli proposal exactly by this function A of gamma and by this BES massless factor. I don't really know why they dropped this guy. So somehow they forgot about this minus sign. So I don't know why. In any case, yeah. Yeah.
The BS factor gives you 1 in the crossing equation,
Yes.
if I remember.
Yes.
And then why do you fix that power? Why do you want to have it? Why
We
not
needed
power?
to have a match with perturbative calculations at 3 level.
And that fixes the power of the BS factor?
Oh, you mean -2?
Yes.
Yeah, -2 is also necessary.
Okay.
Yeah. Otherwise, we will have a mismatch at 3 level.
Thanks.
And as I said, we don't want to use the AFS dressing factor because it has horrible analytic properties. Okay, so that was the story about massless particles. Let's now move to massive particles. And looking at this formula, if you stay at it long enough, you may actually remember this very old paper by Bicert, Hernandez, and Lopez, where they introduce a variable Q to analyze the Hernandez-Lopez dressing phase. And it was defined in this way. And comparing these two equations, you obviously see that there is basically no difference between this gamma and this Q. And as a result, it makes natural to introduce massive gamma plus minus variables in this way. So I take this guy, I just put plus here. And then to define x minus, I complex conjugate this formula so that gamma plus and gamma minus would be complex conjugated to each other if P is real. So that's the story. And then if we analyze these gamma plus minus variables, we find one surprising fact. The crossing transformation for gamma plus minus for massive gamma variables, in fact, is given by gamma plus minus minus I pi, not plus I pi, as it was for massless particles. This can be seen if we use, for example, Z-torus parameterization, because then everything is completely unambiguous. So that's the difference, and the mirror transformation also, as a result, corresponds not to shifting gamma plus minus by plus I pi, but by minus I pi. So there is this difference between massive and massless guys, and that's extremely important to solve the solution crossing equations for massless massive particles. Well, in any case, so these are pictures which show us x plus and x minus planes, physical regions for massive guys. And they are mapped on the gamma plane into these strips, which have width I pi. And in the mirror theory, the physical mirror theory, x plus and x minus have imaginary, negative imaginary paths, and they are mapped into these strips. And as a result, in mirror theory, gamma plus and gamma minus are not complex conjugate. because of that, it makes sense to shift this line here, so that to redefine the gamma variable in the mirror series, so that they would be complex conjugate to each other. So in any case, so if we introduce this kind of natural notations for the difference of these rapidities and write the crossing equations, we find that they are expressed in terms of the same hyperbolic tangent, hyperbolic cotangents of the differences of these rapidities, gamma plus minus. So for massive particles, it is a product of 4 of these functions. For mixed mass, a product of 2 of them. And looking at these guys, and in addition, we also have a monodromy equation, which, if you remember, the right-hand side of the monodromy equation dependent on u variable, but in terms of gamma, it is still of a difference form. And it is also in factorized form. So, and we know how to solve these equations now, right? Because the solution, it is just done by using the same homological functions. All we need to do is to fix a prefactor, a solution of the homogeneous crossing equation, so that it would agree again with perturbative calculations. And these are the factors we find for the mixed mass case. And in fact, there is also a similar formula which relates this guy with the Hernandez-Lopez dressing factor, dressing phase, where the second variable is massless. Okay, so in any case, so if you combine everything, the massive massless dressing factor is given by this formula. And again, we have the BS piece, which is absolutely necessary, and this piece which is also necessary for the agreement. Okay, now we have to solve the monodromy equation, and this can be done by using this function phi hat, which is defined in this way, and it's easy to check that this function satisfies the necessary crossing equation, which involves the sinh function here. So if we do it, if we use this function, then the monodromy equation has a solution given by a product and ratio of all of these functions. And it can be also written in this form, where this function r is given by this formula. So in this ratio and product, these guys cancel out, right? They are not necessary. Okay, so, and once we do it, we can write again the solution for massive dressing factors. And then var sigma plus is given by a product of these 4 functions. And var sigma minus is given by this product and ratio. And again, there are these prefactors which satisfy a homogeneous crossing equation and homogeneous monodromy equation, so it's just a periodic function. And they are again necessary to match with perturbative calculations. And looking at this formula, we actually find that this sigma plus to the minus 2 is just equal to e to the 2I theta Hernandez-Lopez for massive particles. So as a result, we also found this nice product form representation for the Hernandez-Lopez phase, which makes it trivial to do the analytic continuation anywhere you want to. Okay, so well, finally we can introduce some r plus r minus. Well, we need to take product and ratio of this var sigma plus var sigma minus and square root of it. So once we do it, we can write a solution for the massive dressing factors. This is the solution. Yeah, I forgot to mention that sigma var sigma plus appeared to be the same as the previous proposal, so it is the same dressing factors as it was before. Well, in any case, so that's a solution written in this form. And finally, let me just mention that the same solution can be written by using these functions phi plus, phi minus. Right, thank you. It's like 100 minutes for me. That's how I see it. This phi plus, phi minus functions, in fact, can be expressed in terms of one function r. And this function r is just a ratio of a well-known Barnes G function, which satisfies this functional equation. So we do not really need even to analyze all these dressing factors. Everything has been known for decades about them if you use this G function. This representation actually might be important for the mixed flux case. Okay, so let me now do the comparison with perturbative computations, which were done by many people. Well, here is, I suppose, not really a complete list of people who did these computations. And at tree level, our factors match with these computations. Yeah, so it was a necessary condition. So at one loop in the near BMN limit, our factor var sigma minus disagrees with the previous computations. And the disagreement is given by this formula. And in fact, this term can arise just from a local counter term. So it could be due to a Ron UV regulator for the theory. Yeah?
I honestly don't remember. The old proposal, was this disagreement there?
No, there was no disagreement in the old proposal. It was it agreed exactly. Yeah. Yeah, I forgot to mention that these dressing factors have been reproduced recently by using quantum spectral curve after they corrected some mistake in their previous computation. So, so I'm pretty confident that these guys are definitely the right ones. Okay, so so there is a disagreement, but as I said, they can arise from a local counter term, so I do not really worry about them. Then, if you consider the mixed mass sector, then the story is more complicated. So that's what we get for this matrix element, and that's what Sandin and Wolf obtained when they did their computation. And you see immediately that there is a substantial difference. First of all, we see that rational parts are different. So Sandin and Wolf had this extra rational piece, which again can arise just from a local counter term. So it's not really that important. What is much less pleasant is that these guys differ quite substantially. Yeah?
Why could this specify one loop? There's an H without much sense.
1 over h, it's 3 level. 1 over h squared, it is one loop.
There is also a H without.
Yeah, right. So why I call this one loop? That's a good question. Because of this 1 over h squared. But we cannot get rid of log h. Yeah, it will appear always, and I will kind of comment on it in a moment. Yeah. Yes. So we could have removed this h by saying that it is a UV regulator, right? So what is more important here is the difference here and there in the functional form, and that's really a serious disagreement, and it was the same for a previous proposal. Okay, so now Yeah, so actually I just began to talk about it, so let's try to explain this disagreement. So we believe that the reason is in the order of limits, in how the calculation was computed. So in Sandin and Wolf computation, the UV regulator was removed first, and then they removed the infrared regulator, the mass, small mass they gave to the massless mode. Yeah, thank you. But in reality, the correct order is opposite. What we should do, and moreover, we should not remove the UV divergent term, the log of H term at all. We should keep it. And the reason is in the exact dispersion relation. As I mentioned at the beginning, the exact dispersion relation has the square root of m squared plus 4h squared sine squared p over 2. Here I divided it by h, I rescale it for perturbative calculations. And that dispersion relation was a dispersion relation for a lattice theory with step 1 over h. And since it is the exact dispersion relation, the UV regulator actually should be identified with 1 over h. And since h is a coupling constant, even if it is large, we should not really remove it. We should not remove the divergent terms from the calculation. Okay. And then, of course, at one loop, we will get just log of h, right? In a natural way, because it is a UV regulator. So we believe that this is the explanation for this disagreement, and that leads to a necessity to reconsider perturbative calculations. Okay, in the massless sector, the story is similar. We get this result, and that's what Sandin and Wolf got. We see immediately that we have this extra piece. And then we also see that we have still log of h, and then we also have an opposite sign for log p1, p2. Right? Yeah, here plus, minus and plus for Sandin Wolf. And again, right. So and again, I believe that the disagreement is explained in the same way. It's necessary to use a lattice regularization with the lattice step 1 over h, and it's necessary first to remove the IR regulator, and then you get what you need to, I hope. Well, this extra term we got, it comes from this function. And this function actually can be dropped if we consider the scattering of massless particles with opposite chirality. But we believe that it has to be still there. It's more natural. Okay, I guess I do not really have time to talk about the mirror TBA. In principle, it is the standard story by now. Once you have the dressing factor, and once you know how to continue the S matrix and dressing factors to the mirror region, you can immediately write the mirror Bethe-Yang equations, which have this standard form. And then you can analyze them and identify bound states and other string configurations. So formulate the string hypothesis. And then, well, this is the string hypothesis, which classifies what we believe are important configurations contributing in the thermodynamic limit. Yeah, in any case, so this is, as I said, basically the standard story. And this equation I have shown already before. So we just need to take these y functions we have in our string hypothesis. So, and then this is the explicit form of the equations. And again, they have the standard form. In these equations, you see that everything couples to everything. This yq is for left particle. Y bar q, it is not the conjugate to yq. It is a different function corresponding to the right particles. And then we have also y0, which corresponds to massless particles and y plus y minus functions, which correspond to auxiliary roots. In any case, in these equations, everything couples to everything. It's a complicated coupled system of integral, nonlinear integral equations. And then we can ask a question whether we can simplify it. And indeed, we can partially simplify them. And in particular, if we consider yq and y bar q functions with q greater than or equal to 2, then we will see that the equations for these guys decouple. Y plus minus does not appear, and moreover, we get just the same equations as for ADS5 cross S5 case. Similar story is true also for y1 functions, only here it's not really completely decoupled, but again, it's very similar to ADS5 S5 case. So if you forget about these pieces, which we can do if we consider y system equations, then we'll get again equation for y1 function, y system equation for y1 and y bar 1 function, which are of the standard form for ADS5 S5 case. Unfortunately, there seems to be no y system equations of the standard form for massless particles and for y plus y minus particles. At least at the moment, we don't have these equations, and we do not really understand how to derive them. Okay, so let me summarize. So we proposed a new solution to the crossing equations for the pure Ramon-Ramon ADS5 cross ADS3 cross S3 cross T4 superstring. The solution disagrees with known perturbative computations, and as a result, it would be really interesting to reconsider this computation, to use the lattice regularization, which is basically momentum cutoff, and to see whether it would be possible to get what we got. Then the approach of splitting the BS factor and introducing the rapidity, gamma rapidity variables seems to be quite powerful, and it would be really interesting to use it for other backgrounds, like ADS3, S3, S3, S1, or mixed flux ADS3, S3, T4, or maybe eta-deformed ADS3 cross S3 models, where actually the BS path is known. Am I right, Ben? So for there is this Q-deformed BS factor. So for these models, it might be quite possible to find the solution for this model. A similar solution, it would be necessary to modify the gamma parameterization also, I guess. But it's quite, I think it's a doable problem. The mixed flux case is more complicated. And as I mentioned at the beginning, it is quite possible that the pure Ramon-Ramon case is an isolated point. And for non-zero k, it would be necessary to use something very, very different. Well, and then we also derive the Mir-TBA equations, and it's necessary to analyze them. Even though they look kind of similar to ADS5 S5 equations, the properties of these equations are very different because of the massless modes. They change a lot. Still, it's really necessary to study the equations numerically for finite h and maybe analytically for small h. Also to see if the TBA equations resolve the disagreement between semi-classical strings, which was found by Abbott and Aniceta a few years ago. And finally, we can use this, in principle, we can use the TBA equations to derive the quantum spectral curve equations and compare them with the recent educated guess by these two groups. And my belief is that their guess is not quite correct. And it requires some small modification, which would allow to include massless modes. Okay, thank you very much for your attention.
Questions?
So thanks for a nice talk, Sergey. I'm going to start with a very mean question. At some point you said that the dressing factors have now been reproduced from the quantum spectral curve, which makes you confident that they're correct. And you
Only
finished by
massive,
saying,
only massive,
okay,
right? They don't know anything about mixed mass or massless
but
dressing
you're also
factors.
saying at the end that you don't believe the quantum spectral curve is correct. So how's
Yeah,
this a check?
yeah, right. Yeah, so actually when I said they reproduced, I also didn't say it completely correctly. They said that they reproduce these dressing factors if they impose an extra condition of unitarity. And also they said that in principle they can derive these dressing factors, but they have not finished the computation. So, but what I'm saying is that it's most probably what they do should be correct for massive guys. But the modification I'm talking about would be important to see massless modes, which they do not see at the moment.
And then another question, this gamma parameterization you're introducing now, does it get you anything for the BES phase? Does it get you any nice thing, any insight? Or
For the quantum spectral curve?
no, for the BES phase, for example. Like, does it do anything useful?
Well, BES phase is expressed in terms of x plus x minus Zhukovsky variable. You can express Zhukovsky variable in terms of gammas, but it doesn't really help.
Okay.
No, that's this gamma parameterization is really important, for the remaining part. So the BES phase gives you basically the most complicated part of the dressing phase, and this gamma parameterization fixes the remaining part. And they are much simpler than the BES phase. It's we don't expect any problem with this part. The problem is going to be with mixed mass BES phase and massless BES phase because basically these parameters now x plus x minus, they live on the cut, yeah, on the circle, unit circle, and this is a cut on the U plane. And say doing numerics in this situation is quite unpleasant. I just don't know how to do it here.
Okay, thanks.
Hi. Maybe I missed it. So there's this torus that's floating around, and presumably that can be equipped with moduli data.
Right.
And also, you said in passing that the string winding modes have been dispensed with. So I was wondering if both those features can be reincorporated.
Right. So what we are doing at the moment applies only to non-winding modes. So basically, in reality, what we study is ADS3 cross S3 cross R4, not T4. And how to reproduce winding modes, to me, is absolutely unclear. I have no idea how to do it. It would be really very interesting to understand it. But, well, you can't solve everything, right? You should do also something.
So you're saying your TBE will give energies only in zero winding?
Yes, only zero winding mode. Yeah. Well, maybe there is a modification. We don't know. Like, you see, you basically have to change the boundary conditions to account to replace R4 with T4. And in some cases, these boundary conditions can be changed by using these chemical potentials ahead. But honestly speaking, I doubt it would work for this case.
Maybe it's a naive question. In this BMN limit, in which you have half of the fluctuation are massless, for this ADS3 case, I was wondering, you expect that at the perturbative level, all the axioms of integrabilities are satisfied? I'm asking this because there is a recent paper by Dan, Arkady, and Nat, in which they study pure bosonic sigma models, and they observe a production, for example, of particles.
Production of particles.
I mean, if you...
This is an integrable model. There could be no production of particles. Right? The number of particles is preserved. This massless mode, again, as I said, it's probably a wrong name. It's a gapless mode. And so the dispersion relation is fixed by the symmetry algebra. If you believe that there is no anomaly in the symmetry algebra, then it is completely robust. Actually, there is also disagreement between this symmetry algebra prediction for the dispersion relation and two-loop calculation, again done by Sandin and Wolf, where they actually find a correction to the dispersion relation, a strange correction. Again, since I personally do not trust their computation, I don't trust the way they handled massless modes. I think it's fine at the moment, but it's really would be good to reconsider these calculations, because something is really fishy. Either we are very wrong without treatment of ADS3, S3, T4, and there is something really bad happening with the symmetry algebra, or they are wrong with their computation. It's still an open question. Yeah.
So you think using the lattice regulator would fix that problem too?
Yeah, I think so. Yeah. So the idea, in fact, at one loop, I think you do not have to modify the propagator. You can just use relativistic one. I don't think this modification would be important at one loop. At two loops, actually, it should be important also. So basically, it is just a momentum cutoff, right? And you keep the same propagator. But then you first need to take the small mass, the IR, regulated to 0, and then consider large H and keep log H term. Do nothing with it. Yeah? You do not renormalize, you just keep it as it is. And then I believe that it should give the right answer. Yeah, you may need also some counter terms to reproduce this result. It's a difficult computation, definitely. As soon as you have to do lattice calculations, momentum cutoff, it's very unpleasant.
Are there more questions? Then before we have coffee, let's thank Sergey one more time.
Thank you.
Yes? Okay, let's start. So it's a great pleasure to introduce Fiona Seibold from Imperial College, and she will tell us about supersymmetric integrable deformations of ADS3, S3, and T4.
Thank you very much, Ellie. And also first, let me thank the organizers for putting together this nice meeting and for giving me the opportunity to speak. So this presentation, as Ellie said, will be about supersymmetric integrable deformations of ADS3, S3, T4. And this is based on work that I did in collaboration with Ben Hoare and Arkady Zeitlin, who are both in the audience today. So let me start by giving a motivation of why I want to study these deformed backgrounds. So perhaps you can be misguided by the number of talks that you will hear about integrable models, but usually those are very hard to find, especially string theories that are integrable and that have a good target space interpretation. And one instance where they seem to appear quite often is in the context of ADS-CFT, where you have several backgrounds that include the ADS factor that turn out to have this property of integrability. And I would like to, in this talk, to go a bit beyond the most supersymmetric backgrounds of this type and introduce deformation parameters. So this will be continuous deformation parameters that will allow you to go beyond these most supersymmetric cases. But since I would like to still be able to make explicit calculations, I would like to retain the property of integrability and also some amount of supersymmetries. From a from a broader perspective, the two questions that I would like to answer are the following. So the first question is, when you have a bosonic integrable background, so without any fermions, just a bosonic model that is integrable, when can you embed it into a 10-dimensional superstring theory that also preserves integrability? The second question is has to do with the interplay between dualities and integrability. So you know, for instance, that T-dualities, those are dualities at the level of the world sheet, and those will preserve integrability for you. But in the context of supergravity, there is another type of duality that you can consider. This is this S-duality transformation. And you may want to understand, so we know that in some context, in some instances, this S-duality will preserve for you integrability, but we would like to understand a bit better when this happens and why it happens. And in order to understand these questions, I will, in this talk, our playground for this will be the ADS3 cross S3 cross T4 superstring. So the plan of this talk goes as follows. First, I will show you some features of ADS3, S3, T4 that will be important for the rest of the talk. I will then present the deformed backgrounds that we found. In the third part of this talk, I will then argue that these deformed backgrounds are integrable, and this will not be immediate, but it will be made possible by making the relation with inhomogeneous and Baxter deformations. So we have already seen these deformations in the previous days, and here we will use them in order to show integrability of these deformed backgrounds. Then, in the final part of the talk, I will discuss some interesting limits, and I will conclude and give some outlook, some open problems that still need to be answered. So let's start with the first part, and let me give you a brief, present some features of ADS3, S3, T4. So one important feature is that puts ADS3, S3, T4 apart from ADS5 cross S5, for instance, is that you can embed it into supergravity in different ways. So you have you can embed it into supergravity by, for instance, adding a pure NS and S3 form. So you just have H3 form. But you can also have, at the other end of the spectrum of possibilities, you can also have a Ramon-Ramon 3 form. So this is the previous talk was basically sitting here in this pure Ramon-Ramon case. And you can actually have a one-parameter family of solutions where you both have the NS-NS and Ramon-Ramon fluxes turned on. So this is the mixed flux case. and it interpolates between the pure and SNS point. So for this parameter q is equal to 0, and the pure Ramond point where this parameter q is equal to 1. You can, so this will be a one parameter family of backgrounds. You can do more. You can also add 3 parameters in the 5 form flux. This you can achieve by doing TST transformations. And all of these backgrounds turn out to be integrable, and they preserve 16 supersymmetries. So let's also look at the symmetries of the theory. So we know that ADS3 and S3, those are coset models. The symmetry group of ADS3 is given by 2 copies of SU1, 1. So here, whenever I have 2 copies, I will label them by left and right. Similarly, for the 3-sphere, I have 2 copies of SU2. And when I include the fermions in the game, I will have this coset where the symmetry algebra, the isometry algebra is PSU1, 1/2 left times PSU1, 1/2 right. So this we already saw in the previous talk. So here I focused on the curved part of the background. So you also have the torus direction. So we had these factors of U1, but this is just the curved part. I focused on the curved part of the background. OK, so this was some important features that will be important for the rest of the talk. And now let me start by deforming this. So we had this 1 parameter coming from the mixed flux plus the 3 from adding the TST transformation. So let us now add even more parameters by deforming these theories. And one, so also we would like to preserve integrability, and one deformation that we know preserves integrability is TST transformations. So combination of T-duality, a shift, and another T-duality. And this we can do whenever our background has 2 isometries. Now we're lucky because we actually have 4 isometries. So we have 4 factors of U1 sitting in SU1, 1 left, SU1, 1 right, SU2 left, SU2 right. Yes. On the yes. Thank you. Yes. So this is a good precision. These 3 parameters here appear when you do a TST transformation in the torus directions. OK, so we have these 4 factors of U1. So now we will do a TST in the curved part of the background, not including, we don't touch the torus directions. And we will be a bit clever because we know that we want to preserve some amount of supersymmetries. So what we will do is that we will select the U1 factors that belong to only one PSU1, 1/2. So here I will deform the left copy, and I will keep the right copy untouched with the hope that then you will preserve the supersymmetries associated with this second copy. So let us do that. And so this is the metric that you obtain. So this is the metric, the deformed ADS3 factor, the deformed S3 factor, and here I just wrote the torus directions. And so let me give a bit more details about this metric. So when you have this deformation parameter kappa. So this one appears when you do the TST. You have 1 parameter, which is the shift, and this is basically this kappa. When you put kappa is equal to 0, this gives you undeformed ADS3 times S3 times T4. So maybe this is, you don't see this at first. This is because I chose here coordinates that basically make it obvious that, for instance, for the sphere, so this part of the metric, the sphere, the three sphere, you can see it as a S1 fibration over the 2 sphere. So this part of the metric is basically S2, and then you have the fiber Xi1 appearing here. And similarly, you have a similar story for ADS3, where you have S1 fiber over the Euclidean ADS2, or a hyperbolic space H2. And you see, now you do the TST, you turn on this parameter kappa, And you see that the effect of this deformation is to rescale the fibers by 1 plus kappa squared. So this is for the metric. Let's now look at the fluxes. Yes?
So does kappa have to be quantized in some sense here? Because of the coefficients?
Because of the coefficients? No. So this is in the metric. Kappa is just a real number.
Right, but it's entering in the flux as well?
Ah, yes.
So the period has to be integer or something, so is kappa quantized?
So if so perhaps if you do an analysis at the quantum level, it will turn out to have some constraint on it. But for the moment, I'm just talking at the classical level. So I will just assume it to be a real number. Yes. So let's look at the fluxes. So for kappa is equal to 0, so we start from we deform the pure Rameau-Rameau case. So we only have this Rameau-Rameau 3 form that is turned on for kappa is equal to 0. And when we do the TST, yes?
The structure of
P hat
and B hat are different. It's not with the minute term.
So sorry, yes. Yes, it may. Yes. That's correct. Yes, that's true. So we have, when we do the TST, there is another, so there is the NSNS 3 form that turns on, and we see that there is a new 3 form that appears, this DB check, that involves the fibers in this way. So here, this is the usual 3 form that you have for the mixed flux model, that is volume of ADS3 plus the volume of the S3. And the new B field or 3 form that you generate, this will have a different structure. And similarly to the undeformed case, you could add additional parameters by doing a TST in the torus direction. So this was a simple, this was a toy model. We started from pure Rameau-Rameau and deformed it. And what we saw was the appearance of these two different 3 forms. Now, these two 3 forms, they have an interesting property, namely their scalar product and their the scalar product with themselves and with each other is 0. So here, I contract the indices of the 3 forms. And this, from the point of view of supergravity, it basically tells you that it would be interesting to look at linear combinations of these two 3 forms. So we make an ansatz for the supergravity background that includes a linear combination of this dB hat and dB check. So I call the coefficients in front of dB hat by x1 by x, and the coefficients in front of dB check by y, and I populate the NSNS 3 form, Rameau-Rameau 3 form, and Rameau-Rameau 5 form. And I gather then, so then most of the supergravity equations of motion, due to this property, they're automatically realized, but you are left with one equation for the Ricci tensor, and this gives rise to 3 equations. So here I gather all the coefficients x1 to x5 into this vector x. I gather all the coefficients y1 to y5 into the vector y. And we are left with these 3 equations. And if these 3 equations are satisfied, then these fluxes supporting this metric, this is a good, so this solves the supergravity equations of motion. So let me discuss a bit more the properties of this background. So first, let us count the number of parameters that we have. So we had this kappa that appears in the metric. So this is one deformation parameter. And then we have the parameters appearing in the vector x and y that govern the NSNS and Rameau-Rameau fluxes. So we have 5 in x, 5 in y. And then we have these 3 supergravity constraints. And this leaves us with an 8-parameter family of solutions. These backgrounds have interesting properties. So similarly to the undeformed theory, you will have a constant or trivial dilaton. So this is something that I didn't show, but if you write them in terms of a field-bound basis, the fluxes are homogeneous in the sense that they will be constant in that basis. And the geometry has a regular curvature and the vanishing reaches color. So this is very similar to what you have for the undeformed theory. Now, since we did a TST involving the left cartons, the left U1s, we still preserved the symmetries in the right sector. So we still have the SU1, right times SU2 right. And in fact, you can show explicitly that this background preserves 8 supercharges, and these are associated to the copy PSU1, 1/2 that you do not touch when you do the deformation.
So in the left, do you still have the cartons themselves?
Yes, sorry. You have times U1 left times U1 left. Yes.
You can define the energy.
Yes, you can. Yes, indeed. And one way to see these backgrounds that is useful is, and that also, where we have seen one example where this happens, you can see them arising from undeformed ADS3, S3, T4 by dualities. So combining T dualities, so this in fact will be TST transformations, and also S dualities. So in the context of my talk, by S duality, I mean a rotation of the NS-NS and Ramon 3-form fluxes. Now, the question we would like to answer is, what about the integrability of these models? So since it is a combination of T and S dualities, so we know that TST transformations, those we know they will preserve integrability. And in fact, there is a whole subset of deformations that can be obtained from undeformed ADS3, S3, T4 through T dualities only. And those we know for sure they will preserve integrability. However, we also have many other backgrounds that, so the full 8-parameter deformation, some of them will also need a S-duality transformation, and this, a priori, we do not know whether it will preserve integrability or not. So we need to make a further analysis.
So do you know the conserved charges in this case? You know, have a Lux connection?
Yes, I will come to that. Yes. So in order to basically understand integrability of this model, it will be useful to see them not as arising from undeformed ADS3, S3, T4 through T dualities and S dualities, but through inhomogeneous and Baxter deformations through T dualities only. And this will prove for us integrability. So let me come now to this part of the talk where I discuss the relation of these deformed models with inhomogeneous Yang-Baxter deformations. So let me start by saying a few words about integrability in the undeformed theories. So we have the symmetry algebra PSU1, 1/2 times PSU1, 1/2. Algebra, it would be a plus. The Lie algebra has a Z for grading, and the Green-Schwarz string can be seen actually as a semi-symmetric space sigma model on the coset PSU1, 1/2 square mod out by the isotropy, so SO1, 2 times SO3. And so the action is of this form. So here the PI, so P1, P2, and P3 are the projectors onto the different subspaces of the Z4 graded algebra. And this is a group element. And the fact that you can rewrite it as a semi-symmetric space sigma model, this shows for you the integrability of ADS3, S3, T4 in the pure Ramon-Ramon case. Now, in the mixed flux case, you have a similar story, but here, because of this, so basically the fact that you have 2 copies of PSU1, 1/2, you can add a Wess-Zumino term to the action, and this will preserve integrability. So you can introduce this parameter Q, and this will actually show for you the integrability of the mixed flux theory. And then, so this shows that the mixed flux theory is integrable. And now we would like to deform this theory in order to preserve integrability. And this we can do using Yang-Baxter deformations. So this Yang-Baxter deformation will introduce three additional, will add two additional parameters to this action. So it takes the following form. So I didn't write it explicitly, but I give you the structure. So this Yang-Baxter deformation, you add this non-trivial operator between these two forms here. And you see that you have three deformation parameters, kappa left, kappa right, and Q. So this kappa left and kappa right, they deform the PSU1,1 PSU1,1/2 left and PSU1,1/2 right copies. And this parameter Q is associated to the presence of the West-Zumino term. So, and you also see that there is this operator R that appears. So this is the same operator as Sibyl was mentioning on the first day. This is a linear operator that is antisymmetric with respect to the bilinear form, so the supertrace. And it, in order to preserve integrability, we require that it satisfies the classical Yang-Baxter equation, which takes this form. So there are two classes of deformations that you can have depending on what this C is. So C is equal to 0. This places us in the context of the talk by Sibyl, and these are homogeneous Yang-Baxter. This is the homogeneous Yang-Baxter equation if you just put the homogeneous Yang-Baxter deformations. So a particular subset of those are TST transformations and some deformed non-abelian T-dualities. Now, in the case of C different from 0, so when you have this right-hand side, this is the modified or inhomogeneous Yang-Baxter equation, and this gives rise to a new class of deformation, which are called inhomogeneous Yang-Baxter deformations. So let me give two examples. So there is another thing that I would like to say. One is that this action here, you can find the Lux connection, so that the equations of motion are equivalent to the flatness of this Lux connection. So this is a good indication that the model has classical integrability. Another question is about the Weyl invariance of these models. So when you have a string theory, then you deform it, whether you still end up with a Weyl invariant theory. And so there is this unimodularity condition that comes into play. So if you want to preserve integrability, then you have a unimodularity condition on this auxiliary Lie algebra that is constructed using this operator R in this way. And if it is unimodular, then it preserves Weyl invariance. So examples of this operator R. So you have the abelian R matrix. So it's abelian because you take two generators of your Lie algebra that commute. This solves the homogeneous Yang-Baxter equation. So this equation we see is equal to 0. It corresponds at the level of the worldsheet to TST transformations. So you do a T-duality in one isometry. You do a shift with this parameter S. And then you T-dualize back. And this operator is always unimodular, so it will map supergravity backgrounds to supergravity backgrounds. Another type of R matrix that will be very important here is the so-called Drinfeld-Jimbo R matrix. So how is this one defined? You take the Lie algebra, you decompose it into Cartan elements, positive and negative roots. This operator annihilates the Cartan elements and multiplies the positive and negative roots by plus or minus C. So C was this constant that appear on the right-hand side of the the classical Yang-Baxter equation. So this solves the inhomogeneous Yang-Baxter equation. So here I will take C different from 0. Another thing, so it is associated to so-called quantum group deformations. So you will, your symmetry algebra usually is deformed into a quantum group. The unimodularity of the R matrix, this will depend on the choice of Cartan-Weyl basis that you choose in order to define it. So, for instance, for PSU 2,2/4, that is relevant for ADS5, or for the purpose of this talk, PSU 1,1/2, which is relevant for ADS3, STT4, and also ADS2, S2T6, you can show that unimodularity is present only if you consider the fully fermionic thinking diagram of these algebras. So for instance, in our case, we need to look at PSU 1,1/2. This has 3 thinking diagrams. So here I denote this empty node is a bosonic simple root. This node with a circle is a fermionic simple root. So we have these 3 different diagrams depending on the number of fermionic simple roots that you have. And if you want to have a unimodular R matrix, you need to use the Cartan-Weyl basis associated to this fully fermionic thinking diagram. And if you do so, and if you start from a supergravity background, you do the deformation, you will end up again with a supergravity background. So let us do that. Let us apply this do this inhomogeneous Yang-Baxter deformation. And maybe one thing that I should also mention is that, so we have these 2 factors. We have these 2 factors of PSU 1,1/2. We have these 2 deformation parameters. And in order to make the link with the backgrounds that I had before, which I told you preserve 8 supersymmetries, I will only deform 1 copy. So I will only deform the left copy. So I will put this kappa right to 0, and I will denote this kappa left by just kappa. Sorry. So if you do so, if you use this, you do this inhomogeneous Yang-Baxter deformation, then you obtain exactly the metric that you want. So this squashed or stretched ADS3 times S3 times T4. You will get exactly that. Now, for the Ramon-Ramon fluxes, this will depend on the explicit Drinfeld-Jimbo R matrix that you choose. But here, since we know that our backgrounds are supergravity, we will focus on the unimodular R matrix. So we will use the R matrix associated to the fully fermionic thinking diagram. And this gives rise to this background here. So we have NS 3 form, Ramon-Ramon 3 form, and Ramon-Ramon 5 form that are turned on. And exactly those V fields or 3 forms that appeared in the supergravity in the deformed backgrounds that I showed you previously. So we exactly have this structure appearing. And you can actually show that you can obtain all. So we had this picture before where you could obtain these deformed theories from undeformed ADS3, S3T4 through T and S dualities. And now we have another picture. We can actually obtain all of them through T dualities only from this background here, from this Drinfeld-Jimbo deformation.
This is your insight, recent one.
Yes, yes. And this proves for you that the whole family is integrable. All right. So now that I showed you the deformed backgrounds, I argued that they are integrable. Let's look at some interesting limits. Let's see. So when did I start?
About 15 minutes plus maybe.
Okay, okay. So one limit is actually not a limit. It's more an analytic continuation that I would like to consider. So far, I always looked at kappa being real. But I could also look at kappa being imaginary. Now, in the metric, you've seen that kappa appears through kappa squared, so there is no problem there. I will preserve reality. However, if you remember, one of the constraints for the fluxes involved kappa without a square. So if I want to preserve reality of the background, I need to do some analytic continuations. So, and this is summarized here. And what this does is basically, instead of looking at ADS3 as a S1 fibration over the hyperbolic H2, it will just be a space-like fibration over ADS2 now. And the fiber will be deformed by 1 minus kappa tilde square. And so this is quite interesting because you see, so when kappa tilde is equal to 0, you still get ADS3 S3T4, though in other types, not exactly global coordinates, but you still have ADS3 S3T4. And now you can also take the limit kappa tilde going to 1, so that this fiber basically goes to, it shrinks, and you recover the ADS2 factor. So you get a background that interpolates between ADS3 S3T4 and ADS2 S2T6. And you can also look at what happens to the fluxes, and you get ADS2 S2T6 supported by by a 5-ohm flux, for instance. So the usual ADS2 S2T6 that you are familiar with. And throughout, so the whole line, so with kappa tilde between 0 and 1, the whole background is real and preserves integrability and the 8 supersymmetries. So this is quite nice.
Fiona, switching from real to imaginary, could it be interpreted at the level of real form of supergroups on which you formulate your theory?
So, like instead of having for the ADS3, instead of having SU1, comma 1,
exactly,
yes, probably, yes. Yeah. Though, yes, probably, but you still have, you still recover ADS3, so yeah. I'm not. The fermionite sector as well for the
supergroup, if you have a real form, if the real form and the bosonic sector are well classified, at the real form of the supergroup, I don't know whether they are as well. Yes, they are classified by Serganova.
So maybe it's a,
so maybe,
yeah.
Yeah. Because
That's
the fermion contributes, to the.
Yeah, yeah, that's interesting. Okay, so yeah, so it's quite interesting that there is this family of background that interpolates between these two supersymmetric backgrounds, and that preserves 8 supersymmetries. So this, yeah. Sorry. Yeah.
It's good. Kappa is due to TST transformation, right? It's related to the shift.
It's related. So kappa is related.
Or?
So kappa is related to TST in the fibers in the left cartons of ADS3 S3.
It is proportional to gamma. Well, to the shift parameter.
It is proportional. Yeah. I mean, yes. You still need to make a coordinate redefinition. So I don't know exactly what the relation between the shift that you have and in the TST and the kappa. But I mean, they are related, but perhaps they are not exactly the same because you still need to do some coordinate.
So when you do this analytic continuation, gamma becomes purely imaginary.
Yes, it becomes imaginary.
But you also do analytic continuation.
Yes, yes, you also do.
Yeah. I'm just thinking about this Kazakov's model. When they take your imaginary gamma and send gamma to infinity.
The fishnet model.
Fishnet models, right? Is there any relations here?
I don't know.
Okay, what happens if you send kappa tilde to infinity?
Well, but we would like to stay within 0 and 1 in order to have a real background. So yeah, I mean,
so
I know
the background is not real anymore.
Yes,
if
yes,
kappa is greater
yes,
than 1,
yeah.
kappa tilde.
You lose. But yeah.
Okay, thank you.
Thanks. This interpolation, is this only happening in ADS3, or can you do the same thing on ADS5, ADS4? So, because I think the question is, the TST I can view as a beta deformation there very concretely, and then can I match this from going from beta real to beta complex, for instance?
What you asked whether you can go from ADS S5 to ADS S3 in the similar way as we did it now, from 3 to 2.
So from ADS3 to ADS5, for instance,
From
or
ADS5 to
to
ADS3.
ADS4.
Maybe we are pushing here too much. Yes. There is a calculation to be done.
I just have a comment that I guess that here you use crucially the fact that you have this factor.
Yes, of course.
And one factor is related to having ADS2, and that will not quite be the case if you try to go, let's say, from ADS5 to 4 or ADS3, ADS4 to 3.
Yeah, it depends whether you can have pop vibration.
Yes, yeah.
A little bit more subtle.
Good. So let me now consider another limit, and this is to make the link with Jordanian deformations, so a homogeneous Yang-Baxter deformation. So you take, in some limit, you can recover the three-dimensional Schrödinger spacetime, so deformation of ADS3 in the Poincaré patch, with undeformed S3 plus the torus T4. And similarly to what was done here, where you infer integrability through the relation with inhomogeneous Yang-Baxter deformation, this you can also, so you can also infer integrability from starting from a homogeneous Yang-Baxter deformation, so a Jordanian deformation, this Jordanian deformation with the fermionic tail that Sibyl was mentioning on Monday. And another perspective here is that this homogeneous Yang-Baxter deformation, you could also see it as coming from ADS3, S3, T4 through non-abelian T dualities. Another limit is the PP wave limit. So you look at the geometry seen by a particle that moves along a geodesic, so on the a great circle of S3 and also in the time direction of ADS3. And this is the metric that you obtain. And you see that it takes the usual plane waveform. So this coefficient J goes from 1 to 4. And this would be your, so Z1 and Z2 would be associated to the ADS bosons, and this would be associated to the bosons in the sphere. And you see that what happens at the level of the fluxes is that the three forms that you have, they actually coincide. So everything only depends on the linear combination of X1 and Y1. And so you can see this as the geometry seen by so these four free bosons that are massive, and you can compute their dispersion relation, and you get this nice formula where omega is the energy, p is the momentum, and you have two types of particles that are left or right. So this is similar to what we had in the previous talk. And you see that something interesting happens when this x1 plus y1 is equal to 1 plus kappa squared, because then this dispersion relation becomes linear. So you can write it in this form. And so when kappa is equal to 0, you get the usual linear dispersion relation of the pure NS and S ADS3, S3, T4, and you will also have a similar structure while turning on kappa now. Okay, yes. So these are the three limits that I wanted to briefly mention, and so let me now come to the conclusions and the outlook. So let me summarize a bit what I did in this talk. So we constructed an 8-parameter family of supergravity backgrounds that have a deformed metric supported by 7 parameters that control the NS, NS, and Raman fluxes. Depending on whether we take this kappa to be real or imaginary, we had 2 types of deformations. So the 2 types of deformation, and so we had some interesting properties that are similar to what we have for the undeformed theory. Namely, we still have a trivial dilaton, we have regular curvature, we preserve 8 supersymmetries, so we will break half of them, but we still have some good control, and these theories are integrable. We have seen 2 perspectives on these deformed theories. First perspective is looking at them as deformations of, them as obtained from ADS3, S3, T4 through a combination of T and S dualities. And this is not very convenient when you want to investigate integrability, but there is another perspective that is interesting, and this is when you make the link with inhomogeneous Yang-Baxter deformations, and you can then obtain the whole set of deformations through T dualities only. And this provides another example where this S duality transformation, so just this rotation of the NS, NS, and Raman 3 forms, preserves integrability. So this is an example now in the context of inhomogeneous Yang-Baxter deformation. And in fact, similar observation was made in the context of homogeneous Yang-Baxter deformation. And it seems that this tends to happen in all those cases where it happens, you have trivial dilaton and vanishing Ricci scalar. So this is a property that you seem to be required for S duality to preserve integrability. Let me also mention some open questions. So first of all, one interesting question in the context of ADS-CFT has to do with the brain geometry. So we know that for the mixed flux case, or the pure NS, pure Raman, we have a good understanding that these geometries, they can arise as near horizon limits from a brain configuration. And I mean, it would be interesting to understand whether the same happens for these deformed backgrounds, whether we also can find some brain configuration, take some near horizon limit, and end up with these deformed ADS3, S3, T4 geometries. Another question has to do with the symmetries of the deformed theories. So when you have this inhomogeneous Yang-Baxter deformation with 3 deformation parameters, so we kind of know that when there is no Wess-Zumino term, the symmetries have been analyzed in quite detail, and we know that they correspond to Q deformations, so quantum group deformations. But when you add this Wess-Zumino term, there seems to be some tension with that observation. Also, when you want to obtain an exact S matrix based on the symmetries, then you compare with the results from perturbation theory, and I mean, you cannot really find an agreement. So, yeah, what's happening to the symmetries? And so I briefly mentioned the geometry in the PP wave limit. You can, starting from there, you can compute the 3-level perturbative S matrix. But you can, as I said, also try to use once you understood the symmetries, you can try to construct an exact S matrix and then check integrability at the quantum level and apply the whole integrability machinery. And an interesting question has to do, is in relation with this work by a group in Dublin, and I don't know if you heard the talk at IGST from Anna, but they have an S matrix, an elliptic S matrix that interpolates between the ADS2, S2, T6 and ADS3, S3, T4 S matrix. So, and here we have a background that does that, so what is the relation there? And finally, another question has to do with Poisson-Lie duality. So this is something that I didn't mention in this talk, but is inhomogeneous Yang-Baxter deformations, or eta deformations, they're also called. They are Poisson-Lie. They have some special symmetry that is called Poisson-Lie symmetry, and they're Poisson-Lie symmetric to these lambda deformations that Dan was talking about yesterday. And so this is fairly well understood for when you have one deformation parameter, and then it would be interesting to see what happens when you have the whole 3-parameter deformation also, perhaps with Vesumino term. So yes, so that's the end of my talk. Thank you very much.
Questions?
Javier, thanks for a nice talk. So at some point you mentioned a little bit about, at the beginning you started by saying you would like to understand a bit about when S-duality can preserve integrability. Then at the end you said something like, okay, it seems we can do this in the cases where there's no Ricci scalar and so on, and that seems to be a constraint. But I mean, it's also clear that you were able to play this game exactly because you were in this restricted setting, right? That's why you were able to find these backgrounds and show that they're related to integrable backgrounds. So can you really, can you say something more about like excluding other cases? Like, can you show that it's impossible to have integrability or something in some other case where you have S-duality, or?
No, so from this analysis, I don't think you can infer anything about more general cases. And yes, I mean, for this, also to make sense of S-duality as just being a rotation, you need to have trivial dilaton. And I guess, assuming trivial dilaton, and then also assuming that you have homogeneous fluxes, basically having a null Ricci scalar, this is an automatic conclusion of these two constraints. So yeah, yes. I mean, this is another example where it happens, but I cannot say anything about more general cases. Let's say.
Okay, and now you have some larger list of examples. So now you have various kinds of transformations that in the end are related to S-duality. Is there, can you factor out the S-duality and represent it as a chain of other things in some nice way now, or do you not have enough structure yet to see that?
So C, okay, so C precisely at the level of the, so do you mean like C precisely at the level of the inhomogeneous and Baxter deformation? What transformation really is associated to this S-duality?
Yes,
yeah, I mean, I didn't look at it, but it's probably a setting where this can be understood, can be analyzed.
Okay,
yeah.
that would be
You
great.
can ask this question already for the H3 plus F3.
Yeah, just undeformed.
You get some rotation, and you can, S-duality will be some action on this parameter Q. That's all.
Yep, thank you.
Someone else?
Do you have a geometric interpretation for this transformation with kappa squared less than 0, similar to
So kappa square less, yeah, so imaginary, so this is deformation of the, I mean, this will be deformation. So this analytic continuation, you don't do anything on the sphere. So this will again be deforming the fiber, but before we had 1 plus kappa squared. Now it will become 1 minus kappa squared if you think of kappa as just being real.
I mean, can you implement this kappa squared less than 0 transformation on the level of the string sigma model as a transformation of string fields?
Yes. So you need to do, yes. You need to start from writing ADS3, S34 in another set of coordinates where you make apparent that you have this fibration over ADS2 now. And then you do the, I think you should do the TST in another type of fiber that is space-like instead of time-like, and then you should end up directly, I hope, with this background with kappa square less than 0.
So you think it's going to be again a TST transformation?
I think it will again be a TST transformation, just different.
No more questions? Okay, let's thank Fiona again for the very nice talk. And I guess it's lunchtime.